decimal on a string. You need to make a structural breaking change to that event. Well, if you needed to do that with this exact architecture, you'd probably need to update the kitchen service at the exact same time, or in some element of lockstep. You're going to be dependent on the kitchen service handling that new change before you can push it out. Otherwise, you're going to break the system. Doesn't sound particularly evolvable, does it? Doesn't sound particularly loosely coupled. It's important to remember when you're building an event-driven system that the events you publish are the API of your system. So you should treat the events you publish in the same way you might treat a more typical API, a synchronous API. And a really good way to evolve and change synchronous APIs is versioning. Having a way to version your API, to add version 1, version 2, version 3, gives you the flexibility as a developer to change that API when you need to. So why can't you version events? And versioning events is actually a really good thing to do. And there's a really simple way to get started doing this. Instead of publishing that order confirmed event onto a topic called order confirmed, publish it onto a topic called order confirmed v1. So now at an infrastructure level, you're being really explicit about exactly what it is that downstream systems are consuming. They're consuming version 1 of the order confirmed event. And when you need to make that breaking change now, you can start to put separation in at an infrastructure level. You make the breaking change, you need to publish an event of a different structure, publish that to a different channel. And keep publishing that first version as well, which means the downstream systems can evolve as and when they need to. Over time, services can switch over and start publishing the second version, consuming the second version. Now, one thing to be really aware of if you're doing this, you start adding versioning, you start versioning things at an infrastructure level, you start versioning your topics, is to be really careful not to end up in a situation like this, where you keep adding a new version, you keep adding a new version, you keep adding a new version. You're still supporting all them old versions because all the subscribers are still consuming all them old versions. So whenever you do this, whenever you start versioning your events, make sure you set a depreciation date. Set a date you're going to stop publishing that version of the event, and honestly, stick to it. Because once you start letting that lapse, once you start letting that go back and back and back, you're going to end up in a situation like this where you're supporting lots and lots of versions of the same event. So this is one way to do things, to get really explicit, to separate things out at an infrastructure level. But what if you don't have the capability to do that? You're using topics, maybe for a whole range of different message system-to-system communication, but in some cases you might be using a more typical event bus. An event bus where all of the events just go into this same big bus, and subscribers can subscribe to events from that bus. At this point, you don't have that ability to start to separate your events out at an infrastructure level. So if there's one thing you take away from this talk, so one single thing you go and do after you've done this, is to adopt some kind of defined specification for the events that you publish, some kind of defined structure. Something like the cloud events specification. Is anyone using the cloud events specification today? Has anyone heard of it? Okay, a few hands. Cool. So this is the only way to do this. There's lots of different ways. The thing to take away is to have some kind of common defined structure for all of the events that you publish. And the cloud events specification defines a set of properties. The first of those being the data property. The data property is the actual event payload. This is where the order confirmed event that you published earlier is going to go. It's going to go inside this data property. You've then got the data content type. This tells a subscriber what type of data is inside that data property. Here it's JSON, it could be XML, it could be binary, it could be some internal proprietary data format that someone once developed that nobody really understands. You've got the time. This is the time the event was published according to the producer. Now, you could use this to kind of get an idea of ordering, but of course, time and clocks and computers aren't that good going together, so you wouldn't trust it. But it's good to know some element of when things happen before and after each other. You've got an ID. This is a uniquely generated identifier, again, generated at the point of publish by the producer. This allows subscribers to implement things like idempotency, to receive an event and say, have I seen this event before? Yes, I have. I'm going to drop that. I don't need to process it again. And then around this conversation of evolvability, of being able to change the data structures in your system, you've got the source and the type. The source of this event is the production order system, And this is an order-created event. Importantly, it's version 1 of the order-created event. So now as a subscriber, no matter how you receive this event, whether you receive it from a queue, a topic, a bus, a stream, you pop it in a folder on a file system and pick it up again, you've got this ability to understand what this event is. This is version 1, great. We know how to publish version 1, process version 1. This is version 10. What happened to 2, 3, 4, 5, 6, 7, 8, 9? You've got this ability to understand what to expect in that payload. And then one other field I just wanted to point out at this point is this trace parent property. This is what will allow you to do tracing or understand cause and effect inside your system. And we'll talk about observability a little bit more later on. Just know that you can include this trace parent. This here is a W3C trace context. This could equally just be a correlation ID, some kind of common identifier you pass from system to system to understand how things relate together. So once you've got this in place, once you've got this ability to version your events, how does this actually work in practice? So today, you're publishing version 1 of the order confirmed event. And then, actually, you're going to start publishing version 2 of the event. And for a period of time, you're going to be publishing 2 versions of the same event. And at the minute, version 2's sad, it's upset because it's just being published and like disappearing into the ether of the cloud. Nobody really cares about it. But over time, because you set that depreciation date, you say on the 1st of March 2025, we're going to stop publishing version 1, and inevitably, on the 28th of February 2025, everyone's going to panic and eventually move over to version 2, but stick to that depreciation date. Remember that. And remember that the events you publish are the API of your system. So treat the events you publish with the same respect and love and care that you would treat a synchronous API that you're exposing to the public, to another internal system. So congratulations, you've got this ability now to start to evolve your data structures. You've given you as a producer, as a publisher, the ability to deal with breaking changes. You can make a breaking change if you need to. You can publish that in a separate way. You can add that versioning to your events. And you've also given downstream systems more of an ability to evolve independently as well. You don't completely get rid of that, but you do get rid of it a little bit. You give them their opportunity to do things at their own pace. So that covers things you can do at the code level, how you can think about the code you write, the data structures you have, and how you evolve them over time, and practices you can use to do that easier. But when it does come to changing your system, of course, whenever you make a change to a system, you're going to want to test it. And I realize testing is obviously an incredibly contentious topic in software. And actually, one of the most common questions I used to get right when I was working at AWS, talking about serverless and event-driven systems, I'd get people coming to me and saying, well, this all sounds magic, but how do I know it works? How do you test an asynchronous system? How do you test a system that is dealing in the currency of events? And that naturally led to the question, what type of tests should I write? Should I write unit tests? Should I write integration tests? Should I chaos test? What should I do? And actually, for the purpose of this talk, I don't want to get caught up in the semantics of if something is a unit test or if something is an integration test. What I want you to focus on is exactly what it is that you're testing. Not if it is a unit or if it is an integration. What exactly is it that you're trying to test? Which naturally leads to the question, why do we test software? Why do we test the things we build? Whose favorite part of their job is writing tests, just out of interest? Yes, one hand, I love it. Yes, fantastic. And actually a more fundamental question to ask at this point, and I actually want you all to think about this question just for a few seconds. Why exactly is it that you're all writing software? Why is it that you're doing the job that you're doing? Just think about that for a couple of seconds. And I've tried to come up with my own opinions on why I do this, why people do this. The first is to be a little bit more like Scrooge McDuck. Software is a well-paying job, right? It pays well, it's good. Cold hard cash, that's fine, that's okay. The second reason is because we all love building really complex stuff, don't we? We love building cool stuff, we love building complex stuff. It's fantastic, isn't it? It's great when you build something that's really complicated and it works. This diagram actually really makes me laugh whenever I see it, because the first part of my career, I was actually working with SQL Server integration services, building integration packages. Integration packages that used to look at all these distributed systems and all these databases and pull all the data together to make it behave like a coherent whole. Like I was the guy doing the midnight heroics. And I did all of that, and I still ended up being the guy building cool databases and event buses because they were cool, because they were complicated. So we all suffer from this magpie effect of seeing a new and shiny thing and just wanting to build it. Okay, those first two are a little bit tongue-in-cheek, if you didn't gather that already. More often than not, when I think about why I build software, when I talk to people about why they build software, it's because you want to help people. You want to do something that makes somebody else's life easier. And regardless if you're working with a 20-year-old monolith running .NET Framework 1 on a Windows server, or you've got a distributed set of thousands of microservices on a Kubernetes cluster that nobody really understands, fundamentally, the thing you're doing is helping making someone's life easier, more efficient, better. And frankly, if your software doesn't do the thing it's supposed to do, then genuinely, what's the point? Why are we doing it if it doesn't do the thing it's supposed to do? So when it comes to testing, I think this is a really interesting way of looking at things. Does the system do the thing it's supposed to do? And Martin Thwaites, who was just on stage here, he talked about this in a talk from QCon London last year, and I'd really recommend actually going to check out this talk. It's a really fantastic talk on development, software development, testing, and if I try and distill down Martin's thoughts in this talk, and if you are here, Martin, come and shout at me afterwards if I absolutely butcher this. But the thing I took away from this talk is that it doesn't matter if you write thousands and thousands of unit tests that test every single getter and setter on every single property, testing every single method on every single class. If your system doesn't meet the requirement that it has, if your system doesn't do the thing it's supposed to do. And I took away this idea of requirements-driven testing. So thinking about the requirements a system has, a system as a whole, an individual microservice, an individual module, and testing to make sure that the thing does the thing it's supposed to do, that it meets the requirement that it has. And when you think about the order service inside plant-based pizza, the requirement of the order service is that a user can come along, a user can create an order, and then the user can retrieve the status of the order they've just created. And when you think about this synchronous part of the service, you can probably already all picture the type of test that you would write. You can probably almost see the code. You're going to spin up an instance of your service, you're going to create a HTTP client, you're going to make a post request, you're going to make a GET request, and you're going to assert on the results of that GET request. Something like that is probably what you're going to do to test this. But this isn't the only requirement of the order service. The order service also needs to notify other systems that an order has been created. That's a requirement of the service. Remember, you're building an event-driven system. And this last requirement, this thing that you're going to generate an order-created event, well, that order-created event might be being generated to Kafka, to Azure Service Bus, to SQS, to SNS, to whatever it might be. So now you've just got this event that's inside this message channel, and you've got stuff that's happening asynchronously. How do you assert on that? How do you assert on that thing that's happening? And this can get even more tricky when you're dealing with systems that are maybe completely asynchronous in nature. The payment service inside plant-based pizza exposes a queue that only the order service is allowed to send messages to. And when a payment needs to be taken, the order service is going to send a take payment message onto that queue. The payment service is going to pick that message up, it's going to process the payments, and hopefully at some point, going to publish a payment successful event. If the payment doesn't happen, then it will publish a payment failed event. Here you've got an event coming in, an event going out, and actually no real way. You can't hit an API endpoint to check that the payments happen, because that just doesn't exist. Everything is happening asynchronously. Things are starting to sound a little bit trickier now, aren't they? A little bit harder. Maybe you're all now thinking, you know what, I'm going to go to a different talk, I'm just going to build a monolith. I'm going to go and see Glenn's talk from yesterday on YouTube. Build a monolith, build a modular monolith. Okay, so you want to learn about event-driven systems. So there are some patterns that can help you here, some patterns that I've found that have really helped with testing asynchronous systems. And let's come back to this first use case first. If you're running these kinds of tests where you want to test your system does the thing it's going to do, you're probably going to want to run your system in a really isolated way. Whether you're going to spin that up with Docker Compose or .NET Aspire, you're going to deploy it to a staging environment, but you're going to want some element of control over the environment that's under test, the system that's under test. So as well as spinning up your service in some way, you're probably going to also spin up some kind of database. You're probably also going to spin up some kind of event bus. You're going to spin up all this other infrastructure that you need to actually test the system under test. And you probably also, if you're in this situation where you're storing state in a database and you're publishing an event, you're probably going to be using the outbox pattern. Who's familiar with the outbox pattern, by the way? I've heard it mentioned a few times this week. OK, cool, most of you are. For those of you that aren't, the outbox pattern simply is when you write some state to your database, you update the state, you also write any events that you want to publish to a separate table in the database. And you wrap both of them things in a transaction, so that if one happens, one doesn't happen, the other doesn't happen either. This avoids being in a situation where the state gets updated, but the event doesn't get published, or the much more tricky, the event gets published, but the status doesn't get updated. So because at this point, you're in a situation where your state's been updated and a record has been written to a database table. So at a really simplistic level, one thing you could do to test this is to check the outbox table in the database to make sure that the record has made it to the database. Because then some separate process is going to come along later, it's going to pick up that event and publish that event. So surely if the record gets written to the outbox table, that categorically means that that event is going to be published. I'm sure you can all imagine ways where this would be tricky, but if this is the place where you're at today, you've got a database, you've got an outbox, you can't think of another way to test it, this is one such way you could do it. You could simply query the database and check a record has made it to the outbox table. But if you think about the requirements of the order service, the requirement that you have to build into the order service is not that a record gets written to a table in the outbox. The outbox is an implementation detail inside the order service. The requirement of the service is that an order gets created. An order created event gets published. Other systems are notified that there's a new order. So this is a good interim option. I think there's a better one. So when you set up that service for testing, you're going to spin up your service, you're going to start up the database, you're going to start up some kind of message channel. And actually, you've got an opportunity here. You've got an opportunity to start doing a kind of mocking. Is anyone here familiar with WireMock, actually? A service called WireMock? OK, some of you are. So WireMock's a really cool service that you can use to mock synchronous APIs. So if you're testing service-to-service communication, it's a really cool way to do that. And you can take that same thinking of, actually, I'm going to mock a synchronous API that I want to communicate with, and I'm going to mock a subscriber. So I don't know of any tools that actually do this. So this would require a little bit of building yourself. But you can build a system that when you spin up your service for testing, you're also going to spin up a service that simulates how a subscriber is going to behave, that's going to subscribe to all of the events that you are publishing. That's the requirement that your system has, remember, to make sure that order-created event gets published. When you work through actually writing that test now, so you want to test that when a create order request is received, that an event gets published. That's the requirement of your system. So you're going to spin up all this infrastructure, you're going to spin up your services, and you're going to start in the same way. You're going to make that post request, that synchronous API request to the order service. The order service is going to come back, say that was order 1, 2, 3, 4, 5, 6. It's going to give you some kind of unique identifier. Event's going to go into the outbox table. It's going to be picked up from the outbox, published to the event bus. And then your test harness, this additional thing that you spin up, can subscribe to them events and hopefully receive that order-created event that you've just published. Now you're actually testing that the event that you said you're publishing you're publishing that event to the channel that you said you would with the right name. You're testing that the event actually makes it. Then with this test harness, you can start to expose a synchronous API endpoint, an endpoint that allows you to retrieve all of the events that have been received, which allows you in your test to assert on the fact that an order-created event has been received for order 4356, or 12346. So this is one such way to do it, and you can build these test harnesses in a way that are reasonably generic. And there's a GitHub repo in here somewhere that actually has an example of how to do this with plant-based pizza. And if you take this same way of doing things, this ability to mock out a subscriber, you're mocking to make sure that the event gets delivered to the place that you think it should. And then if you think about your fully asynchronous use case, where you've got an event coming in and an event going out, you can apply this exact same pattern. You've got this practice in place now of just spinning up a test harness. So you can start up your payment service, you can start up the queue that the payment service is hooked up to, and you can inject that take payment command. The payment service is going to go off and do its work. It's going to take the payment. Then it's going to publish, hopefully, a payment successful event, if that's the thing you're testing for. It may even publish a payment failed event. The test harness consumes that, and then you can start to assert on the fact that the test harness has received the event you expected it to. So up to now, you're testing the happy paths. You're testing that the service does the thing it's supposed to do, which is a fantastic place to start. Who's here written a system that has never, ever failed? okay, it's good. You're all in a safe space. You're all okay admitting failure. It's good. It's nice. Because sad paths happen as well, don't they? Things go wrong, probably more than they go right in some cases, at least with software I'm writing. So you want to test the sad paths as well. And there's a lot of sad paths that can happen in event-driven architectures. Maybe an upstream system publishes an event with a different format. They make a breaking change, and they decide not to tell you. How does your system handle that? Maybe you need to implement idempotency. Maybe you need to check that if you receive the same event twice, that you don't process it twice. And if you think about a requirement of the payment service, if you were to order a pizza and get charged for that pizza twice, 3, 4 times, unless you were going to receive 4 pizzas, then you probably wouldn't want that to happen, would you? So there's a set of things that you can actually test for. You can test for the sad paths. And once you've got this ability to behave like a subscriber, to have this test harness, you can start to test these things quite easy. You can test that in your payment service, if a message is received twice for the same order, that you don't process that payment twice. You can inject a take payment message into the service, and then you can immediately inject another take payment message for that exact same order. And what you're going to expect, the requirement of your system, is that one payment successful event comes out the other end, which allows you to write test code that looks a little bit something like this. You can spin up your infrastructure, you can start up your service, and then you can inject 2 instances of that same take payment message. You're going to generate an order identifier for the order that's under test, and you're going to inject one take payment message, and then you're going to immediately inject another take payment message with the exact same order. And then because you've got this test harness in place, you've got this ability to understand what comes out the other end. Does the system do the thing it's supposed to do? You can then assert that you only receive one payment successful event. So now you're starting to test the requirements that your system has. Now, if some of you may already be thinking that there's a problem with this approach, there's something that can go quite easily wrong with this approach, something that's really frustrating, and that's flaky tests. Tests that sometimes work, sometimes don't, sometimes they work, sometimes they don't, and that's, well, because these things are happening asynchronously. Your test is taking an action, and then maybe sometime later an event is going to come out the other end, but you don't know how long that's going to take. When you run that locally, it could be milliseconds. When you run it in Azure or AWS, that could be hundreds of milliseconds. Which means whenever you're writing these kinds of tests, you're always going to need the ability to retry, to check to see if an event has been received, to assert an event has been received, and if it hasn't, wait and try again, and wait and try again. And, of course, you're probably now thinking, do you just do this ad verbatim for infinity, and you just have an impossibly long-running GitHub action that's always waiting for that payment successful event to come back? And, of course, you're not going to want to do that. You're going to want to have some kind of cutoff. You're only going to want to retry a max number of times, which then naturally leads to the question, how long do you wait? How long do you wait for that success or failure event to come back? And actually, a really nice way of doing this is to think about, again, the requirements that your system has. If you need to process payments inside 200 milliseconds, 100 milliseconds, use that requirement that your service has for latency to judge how long you're going to wait for the event to come back, because then you're both testing that your service meets the SLO that it has, whilst also testing that the event gets published as you expect it to. So maybe that's 200 milliseconds for the payment service. You might check once, wait 100 milliseconds, check once, wait 100 milliseconds. Maybe you give it another 100 milliseconds, and then you fail, then you drop out. And that's obviously going to change based on what exactly the requirements of your system are. So up to this point, we've talked a lot about flow, events flowing around, checking that a system publishes an event, sends a notification to the place that you expect it to. But if you think back to that issue I had right at the start of the talk, that wasn't an issue of flow, that was an issue of structure, how events are structured. And you can test for this as a subscriber. You can test for the fact that an upstream system might make a breaking change to an event that publishes and breaks your system. But that test is probably going to go as far as, I receive an event, I don't have a clue what any of this is, I'm just going to store it in a dead letter queue. That's probably the extent of how you can test your system. You can test breaking changes of upstream systems. But is there not an opportunity here to shift some of this testing into the responsibility of a producer? And actually, one of your responsibilities as a producer in an event-driven system is to not make breaking changes. And if you're going to make breaking changes, do it in a way that's evolvable, that's controlled. So one of the things you can do in a producer is you can actually start to test the structure of the events that you publish. You go off and you start writing a test for your order service. You write a test that's actually going to run a piece of business logic and check that the event that gets generated matches the structure that you expect it to. So you're going to run this order.create method. And the way all the eventing works inside this application is that whenever anything happens against an order or any entity, the events get collected up in an in-memory list. And then when that record is written to the database, when the state is updated, you're going to open a transaction, update the state in the database, iterate through all them events that the object's got in memory, write them to the outbox, commit the transaction. So when you run this piece of business logic, order.create, the first thing you're going to do is check that there's an event in that list of events on the object that is an order-created event. So if you imagine a new developer comes along, they make a change to this, they add a new order-create method, they forget to generate the event into in-memory, this test would at this point fail. So you're testing that the business logic is generating the event that you expect it to. But you can take that one step further. You can take that event that is being held in memory, and you can serialize that to a string. And then you can use a really wonderful NuGet package called njson schema. And I don't actually know if system text JSON does this, actually. Maybe it does now. But you can use njson schema to load up a JSON schema. And then you can validate that JSON schema against an actual JSON string. NJSON schema is going to give you back a list of validation results. And then you can assert that the count of the validation results is 0, which means the string that's been generated, the JSON string, matches the schema that you've given it. So if you were to come along now and think, wow, that order identifier property, I want to change that to order ID because it's shorter. Shorter. That would then break this test. The first bit would still pass, but the second bit, where you're testing the schema, would fail. So now you're starting to test this as a producer level. As you as a producer are making changes to your system, you're writing tests to make sure that the event you generate matches the schema that you expect it to. So you're in a good place now. Good job, everyone. You've got this ability to evolve your code. You've thought about versioning your events. You've thought about how you're going to evolve your data structures. You've got the cloud event specification. You've written tests to test how events flow around, to test that you aren't making breaking changes to your events. And then you deploy all of this, and everything still fails. Everything is still going to go wrong. One of the second most guaranteed things in software, as well as change being number one, is failure. Systems always fail. Which brings us to probably the most important part of modern distributed systems development. Frankly, any software development. And that is observability. Being able to observe your system. Distributed systems are being changed frequently by different teams of people with different release cycles, different SLAs, different levels of experience, different technology stacks. There is no possible way you could predict every single way your system could possibly go wrong in production. So what do I mean by observability? How do I think about observability? I think about it as the ability to ask questions of your system. Questions that you didn't know you needed to ask from a location that is outside of your system. Questions you didn't know you needed to ask. It's got a strange way of putting it, isn't it? How can I ask a question I didn't know I needed to ask? And if you think about the components of plant-based pizza, and imagine you're a developer on the order service and you have an outage in the order service. And that outage is caused by the database going offline. Maybe the database server ran out of disk space, for example. So you're going to go along as a developer, you're going to hopefully increase the disk space of that database server. Thankfully, you're running on the cloud, so you can just give it more disk space, and that's relatively easy. Database comes back online. Maybe I'm oversimplifying that. Hopefully, after you've done that, you're going to have some kind of retrospective. You're going to look at why did this happen, how did we let this happen, and you're probably going to put some kind of monitoring in place. You're going to monitor the disk space of that database server. And then if the disk space gets above 80%, you're going to tell somebody about it so they can preemptively go and resize that database server. The problem with this is that the chances of this exact same issue happening again in the exact same way is now dramatically reduced because you've got a thing monitoring it. But because you've got all these different teams of people changing systems at their own frequency, at their own rate, you are dealing with unknown unknowns. There is no possible way you could predict every single way your system could possibly go wrong. There's no way you could test for every single possible way that your system could go wrong. And this gets even more difficult when you're building event-driven systems. Because not only now have you got systems that are being frequently changed by different teams of people with different priorities, different release cycles, these systems are also now communicating completely asynchronously, which makes cause and effect incredibly difficult to understand. How do you understand the systems that are upstream of you, systems that you're dependent on? And equally, possibly even more important, how do you understand the systems that are downstream of you that you're going to impact? And when you compare this to a synchronous system, imagine you were back in the days where you used to have synchronous API calls. Here, cause and effect is relatively easy to understand. The order service is going to make a call to the kitchen service on kitchen.plantbasedpizza.dev, whatever. It's going to block, it's going to wait until there's a response. The response is going to come back at some point. That might be a 200, that might be a 500, it might be a timeout even, but the order service is waiting for the kitchen service to do something. Here, you can reasonably easily infer cause and effect. You can infer that the order service is affecting the kitchen service. But when you think about your event-driven system, well, here, producers are just producing events, they're sending the events out, getting on with their day. Subscribers are subscribing to events, hoping, praying that an upstream system doesn't make a breaking change. It's much more difficult to understand cause and effect, which makes tracing, or distributed tracing, probably the most important thing to think about in asynchronous systems. And just a level set to make sure that we're all on the same page in terms of terminology. At the very top level here, you've got a trace, or a root span. The trace is the overall end-to-end flow of a request. A trace can be made up of lots and lots of different spans. These spans can span multiple different back-end systems, multiple different services. Now, to add a little bit of nuance to what I've just said that tracing is the most important thing you need to think about. To caveat that, though, that's tracing with context. You can add tags to these spans, you can add attributes to these spans, and it's this context that allows you to ask the questions of your system that you didn't know you needed to ask. Context is the key part of modern observability. Whether you're using traces, whether you're doing structured logging, context is key. And I like to think about context in two different ways, two different parts to context. The first is technical context, context that's going to be the same across every single system that all of you are building. What was the HTTP route? What was the method? What was the status code? And OpenTelemetry actually publish a set of semantic conventions for messaging, which is best practices between you and me. And these best practices define a set of tags, a set of attributes that all spans related to messaging should have. That covers things like the operation name. Are you sending a message? Are you receiving a message? Are you processing a message? That includes the messaging system. Are you using SQS? Are you using Kafka? Are you using SNS, Event Grid? And what is the actual thing that you're sending to? What is the name of the queue, the topic, the stream? And there's a whole bunch more semantic conventions, and that QR code will take you to the page. I didn't want to put them all on the screen because it'd get very, very busy. Now, these two at the bottom here, at least last time I checked, these two at the bottom here aren't in the semantic conventions for messaging. But these are two I always like to include myself. What is the version of the message that I've just consumed or I've published? And what is the type of message that I've just consumed or I've just published? And once you've got this technical context, you've got this common set of attributes that all spans in your system related to messaging have, you can start to then infer and aggregate your trace information to give you some really nice high-level information about your service. How many messages am I publishing? How many messages have I consumed? What kind of throughput does my system have? What's the age of the last message that I processed? What's the average size of the message that I'm processing? So once you've got this common set of technical context on your spans, on your telemetry, you can then start to infer really useful information about your system. But this is only one part to context. This is technical context. This is context that all of you will have in all of your systems that you're building. The more important half to context is your context, the specific context that your system has. Things like the user ID, the order ID, the number of items on an order. You want to add as much context as possible to your telemetry, because it's that context that's going to allow you to ask questions of your system, to ask the questions you didn't know you needed to ask ahead of time. Imagine your support team comes to you and they say, someone's just rung up, they'd ordered a pizza, and the pizza never got to them. Now, that would be an incredibly sad place to be as someone who's just ordered a pizza. But you're going to have to figure that out now as a developer. And I'm sure you've been there, where you've been in that situation where the support team comes to you and they say, hey, we've got this issue, and you just go, ha, 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 that's a good one, I don't have a clue. Having this context allows you to start to ask these questions. Where was the last place I saw some telemetry for this customer, for this order? Maybe it seems like, actually, when an order has more than 15 items, things start to go wrong. Can I aggregate my data to look at that? You can start to ask these questions of your system. A company I used to work for, we used to have this question in the pull request template. Whenever you made a PR, you wanted to ship something to production, you had to answer this question. How will you know that this specific piece of code you've just written has reached production? More often than not, this was implemented using span tags. You would add a tag to the currently active span. That code reaches production. You can then run a query in your observability backend to see, well, is this code in production? Yes, it is, because this tag I've added has made it to production. One thing I always like to point out at this point, when you're adding contextual information to your telemetry backend, please don't add any sensitive information to your observability backend. What I really don't want is all of your security teams ringing me up in a month's time saying, well, one of our developers saw you speak at NDC London and used data to add a lot of context, and now we've got credit card information all over our observability backend. Please, people, don't do that. Don't send credit card information to your observability provider. That's not a good thing to do. So tracing seems like it's a little bit of a silver bullet, right? It gives you this ability to understand cause and effect, to understand how one system impacts another. And you look at these trace graphs you get, these lovely trace graphs that say, hey, well, look at all these back-end systems that are involved. Look at this trace information being propagated from service to service to service. It looks great. I mean, it looks pretty. It's colorful. And you can even start to zoom into this information. You can zoom in and say, actually, show me exactly what is happening in my system. This specific instance of plant-based pizza was deployed to AWS, and you can see that this message spent 294 milliseconds inside an event bus, inside Amazon EventBridge. It then spent 117 milliseconds inside an SQS queue before it was eventually picked up by a Lambda function. And you can see, wow, this looks really useful, right? I can see all this contextual information. And to get this level of contextual information, you're probably going to have to do a little bit of work yourself. So SQS, as an example, when you receive a message from Amazon SQS, in the attributes, you will get a header that tells you when was the time SQS first received this message. And then as Martin started to show you earlier, you can generate a span that gives you that length of time. How long is it since SQS received the message? What time is it now? Here's how long this message spent in flight. And some observability providers will actually allow you to automatically generate this level of context. But looking at this screenshot again, there's something else in this screenshot that's kind of confusing. You've got all this colorful stuff, you've got this bit at the start, and then you've got this really long purple bit. This really long purple bit that takes a disproportionate amount of time relative to the rest of the request. And in this instance, this is a third-party API call that your system needs to make, and this third-party API can take a little bit of time to respond sometimes. And many of you will have situations like this. You'll have situations where an event gets generated, that event starts some kind of long-running business process that might take minutes, it might take days, it might take months even. And you've got a slightly different instance of this inside plant-based pizza. Every day, you run a daily job. That daily job is going to take all the orders that were confirmed that day and run some kind of analysis on that set of orders. And if you were to simply just propagate the trace, you were just to propagate the trace so you could see it in that big, long flame graph. When you came along to debug the daily job, to understand what was happening in the daily job, well, all those individual spans are going to appear in the upstream service traces, which isn't particularly useful for you as a developer trying to debug the daily job. This also gets really confusing in the other direction, though. Because imagine someone had placed an order for a pizza at 9 o'clock in the morning. Pizza for breakfast, that should happen more often if you ask me. But someone ordered a pizza at 9 o'clock in the morning. This daily job runs at midnight, and that then gives you what is in effect a 15-hour trace. Don't ask me about if that maths is right. So as you're a developer looking at the order service now, you're going to see this trace that started at 9 o'clock in the morning, then 15 hours later there was a load of white space, and then the daily job ran. So it's not actually helpful to always propagate trace information, to always just continue the trace through every backend system. But thankfully, there's another thing you can do. There's an alternative approach called span linking. In span linking, you can keep things independent. You can keep independent traces that are relevant to your system, your debugging context. And you can say this span in this trace links to this span in this trace, which allows you to keep things independent. It allows you to keep independent traces for independent services to add context that's useful to you, whilst still understanding cause and effect, to understanding how systems are impacting each other. Which will probably lead to some of you asking the question, which is the right one to choose? Do I propagate traces? Do I link spans? And one general rule of thumb I tend to use for this, and of course nothing is absolute in software, but this one rule of thumb I like to use, is that inside a given service boundary, inside a service that you own, propagate trace information. Think about that outbox pattern. A request comes in, you're going to write it to the outbox table, something else is going to pick up and process that message from the outbox and then publish it. Propagating the trace, having one continuous trace through the outbox and out to the event bus is probably a useful thing for you as a developer. But then when it comes to inter-service communication, you've got the order service now publishing that event that the kitchen service is consuming, a lot of times it can be useful to link at that point. So as a general rule of thumb, linking between services, propagating inside a service, can be a really good way of thinking about it. But of course, these things aren't absolute. And whichever way you do it, whichever way you're building an event-driven system, pick one or the other, because when you pick one or the other, it allows you to start to understand your dependencies. It allows you to look at the product service inside plant-based pizza and understand that the pricing service is an upstream dependency of the product service. And it also allows you to understand that you've got this whole range of other services that are downstream dependencies of the product service. You can understand cause and effect. Observability adds the required nuance to this statement. And I think this is a really dangerous statement sometimes in event-driven systems, that services are unaware of the downstream consumers of their events. And whilst technically this is true, technically systems are unaware of the downstream systems of their events, you probably should care about who is dependent on you and who you are dependent on. So to start to bring all this together now, how many of you are familiar with the idea of API-first design? Okay, a couple of hands. The idea of API-first design is that, imagine you're building a system, you've got a front-end team and a back-end team. The first thing you're going to do before you write a single line of code is design the API, design the contract. That way, teams can go off and work completely independently, and then when it comes to integrating the thing together, theoretically, things just join together again, theoretically. Which means when you're building an event-driven system, given that the contract of your events, the schema of your events is the tightest form of coupling you will have in your system, is that really you should practice event-first design. Be really intentional about the structure of the events that you publish, because that is the tightest form of coupling. And as you've learned in this talk, there's techniques you can have where you can evolve these event structures, using things like the cloud event specification, using versioning. And you can test for this as well. But you might also start thinking, if the contract of my events, if the structure of my events is the tightest form of coupling, wouldn't it be great if we could just add the contents of an event to our telemetry? You think, why don't we just start logging all of our inbound messages, or adding them as attributes to traces, adding our entire event payload to the structure in our telemetry backend? And if you do this, every time somebody does this, a security person somewhere in the world has a heart attack. Because you're now just blindly storing information about an event inside your telemetry backend. And this comes back to the point I made earlier. Be really careful about what you send to your observability backend. You don't want to be putting sensitive information inside another system, outside of your system. Unless, of course, you've got permissions to for whatever reason. But I do think there's something here. If the contract of the event is the tightest form of coupling, and of course you can document event-driven systems, you can write documentation gets out of date, as you all well know. So why can't you take that event you receive, and you've already seen how you can take a JSON string and generate a JSON schema off that. The NJSON schema library allows you to take a JSON string and generate the schema of that piece of JSON. So what you can do is, instead of adding to your telemetry the actual event contents, which in a lot of cases is something you probably don't want to do. You can add the structure of your events to your telemetry backend. This allows you to start to play detective, to start to ask the questions of your system that you didn't know you needed to ask. You can ask your system, well, we've got this event that was successful, this event that's failed. Let's have a look at the diff of the schemas. Okay, we know it's not somebody making a breaking change. There's something else going on. You can ask the questions of your system. So at a code level now, you've built in the ability to evolve your systems, to allow you as a producer to evolve your events, to deal with changing requirements. But you've also given your subscribers, the downstream systems of yours, the ability to evolve independently as well by using versioning in your events. And you've written tests that allow you to test both the event flow, how events are moving around, but also the structure of these events, that they meet the requirements that you said that it would have. And finally, you've learned that observability is incredibly important. Adding context to all of the telemetry inside plant-based pizza is a really useful thing to do. Now, I know what you are all thinking. I'm not actually a developer of plant-based pizza, am I? As much as it'd be great to work on a pizza restaurant that probably gives you free pizza, hopefully. You've all got your own Jira backlogs. You've all got your own issues. You've all got your own product managers. What does this actually mean for you? As you walk out of this talk today, what are the things that you should actually take away and do? And the first is to adopt some kind of specification for your event structures. Give yourself this ability to be really intentional about how you structure your events. Include these properties, include the ability to version events, and including it in the actual payload itself protects you from a situation where maybe you're using a messaging technology where you can't start to separate things at an infrastructure level. Remember that context is king. It's context that gives you that ability to ask questions of your system, to understand exactly how your system is working in production. And finally, think about things both at the micro level, at an individual request level. Obviously, it's incredibly useful to be able to track an individual request as it ping-pongs and bounces through all these different services. But don't forget about the bigger picture. Don't forget about aggregating this information and looking at a high-level look at your system and how your system is performing. Event-driven systems are an incredibly good way to build modern distributed systems. If you're adopting microservices, if you're breaking your systems down, event-driven architecture gives you that ability to have loosely coupled communication, to let systems communicate in an asynchronous way. But it isn't without its trade-offs. Event-driven architecture can lull you into a false sense of security, make you think that you're more evolvable than you actually are, make you think that your coupling is looser than it actually is. It can give you a false sense of security about the fact that you can just make changes to your system. You can just change an event, and you don't really need to care about these other systems. You can just make a breaking change. And once you've made a breaking change and broken a system that you didn't even know existed, honestly, it's not very good for business. And genuinely, it's not actually a really good way to make friends. If you found this talk interesting, I have a course on Dome Train that goes through end-to-end building an event-driven system in .NET. I've also got a whole lot of content on my YouTube channel. If you're interested in event-driven architectures, there's a whole lot of free content there about building event-driven systems in .NET. Plant-based pizza is a real application. I used to give this talk, and it wasn't actually a thing, and then I built it. So there's an implementation on that GitHub repo in AWS. So you can deploy it to AWS, you can deploy it to Azure, you can run it as a monolith. There's a whole lot of different implementations in that QR code. And finally, I know it's late on a Friday, so I do genuinely appreciate you all sticking around, listening to me ramble for an hour. If you've got any questions, I'm going to head out to the particular booth just to get out of the way so that Rendell can come in for the keynote. So if you've got any questions, come and catch me over there. And thank you all very much for listening.